Good afternoon, students. Today we are going to discussing paper 7 to unit 12. Synthesis of five-membered heterocyclic cyclic compounds more than two heteroatoms. Some of the important five-membered ring heterocyclic compounds more than two heteroatoms, including oxadiazoles, thiazoles, triazoles, and tetrazoles. Derivatives of these heterocyclics are stable aromatic compounds have been used commercially as a pharmaceutical and dineshifers and pesticides. First, we are going to discussing one of the heterocyclic is oxidizole. These oxadizoles are generally three are there, three types: 1 to 4 oxidizole, 1 to 5 oxidizole, and 1, 3, 4 oxidizole. So first we are discussing 1 to 4 oxidizoles. These 1 to 4 oxidizoles are synthesized by the acylation of amidoxymes and imidoxymes. Amidoxymes in terms are obtained from nitrile and hydroxylamine. When nitriles are under reacting with hydroxylamine, then forms amidoxymes. These amidoxymes under reacting with acid derivatives, acid halides. When this acid halides, chlorine reacting with amidoxymes oxygen atom, then forms OSL amidoxymes. OSL amidoxymes undergo heating, undergo rearrangement, then gives 1 to 4 oxidization product will be formation takes place. So another example for this 1 to 4 oxidization as given here: aryl sulfoxyl estronitrile. This aryl sulfoxyl estronitrile reacting with hydroxylamine then gives an amidoxime. This amidoxime is acid halides in heating, then forms 1 to 4 oxidizole will be formation takes place. Second method is acylamide obtained from obtained from amides reacting with hydroxylamine to obtain 1 to 4 oxidizole product. So this amides, primary amides reacting with dimethoxymethylamide then gives acylamide. Then acylamide under react with hydroxylamide undergo cyclization, they gives 1 to 4 oxidizole. Third one is 1, 3 dipolar addition reaction of benzonitrile and aryl nitrile N oxide. Benzonitrile and aryl nitrile N oxide under heating then gives 1 to 4 oxidizole will be formation takes place. Reactions. Oxidizoles are very weak bases due to negative minus I inductive uh, effect of external heteroatoms. Electrophilic substitution reactions are unknown except halogenation and mercuration. When oxidizoles reacting with mercury chloride in presence of sodium acetate at room temperature 1 month, mercuration takes place at fifth position. This mercury chloride of oxidizole 1 to 4 oxidizole reacting with iodine then gives 5 iodo 1 to 4 oxidizole product will be formation takes place. So halogen nucleophilic substitution reactions, halogen at fifth position are more reactive than that of third position in nucleophilic displacement. That means 4 halo, 4 chloro, 5 chloro, 1 to 4 oxidizole reacting with incoming nucleophile Y replace the chlorine atom at fifth position. If chlorine atom at third position also involved in the nucleophilic displacement, but it is very less reactive than that of chlorine atom involved in nucleophilic displacement reaction at fifth position. The nucleophilic attack of the oxidazoles at unsubstituted ring carbon often lead to ring cleavage. The ring cleavage reaction. Then hydrogen of 3-ethyl 1,2,4 oxidazoles undergo rearrangement on heating to the melting point. Then gives 1 to 3 triazoles are the products. Next 1 to 5 oxidazoles. When these 1 to 5 oxidazoles are synthesized by cyclodehydration of 1 to bis oximes. 1 to bis oxime upon heating then forms 1 to 5 oxidazoles. And reactions. Base catalyzed deprotection occurs readily. This may leads to ring cleavage. And when hydrogenate with third position of 1 to 5 oxidizole, they subtract the hydrogen from third position, then negative charge will be takes place. This negative charge involves in the ring cleavage. So C-methyl group can undergo metallation. If methyl group at third position of 1 to 5 oxidizole, when reacting with the base like n-butyl lithium, that lithium n-butyl lithium abstract the base proton from methyl group attached at the third position of 1 to 5 oxidizole. This negative charge involving reacting carbon dioxide carbohydrates, then carboxylic acid formation takes place at methyl group. So next one, rearrangement reaction of or-ring cleavage reaction. Here we are discussing here. Changing the position of oxygen atom attached to nitrogen on 1 to 5 oxidizole from right to left side. 1 to 4 oxidizoles. 1 to 4 oxidizoles. A cyclic dehydration of N-diacyl hydrogen. N-diacyl hydrogen then gives 1 to 4 oxidizole. 134 oxidizole. 134 oxidizole. By oxidative cyclization of SL. Then SL hydrogen reacting with the good leaving group, then undergo 1,3 dipolarization reaction. They forms 1, 3, 4 oxidizoles. By heating tetrazool with acyl reagent, 1, 2, 3 tetrazoles reacting with acyl derivative in presence of pyridine. 2 acyl derivative of tetrazool will be formation expressed. These 2 acyl derivative of tetrazool undergo loss of nitrogen gas, then forms 1, 2, 1, 3, 4 oxidizole will be formation takes place. Reactions. Nucleophilic displacement of a good leaving group on carbon atom occurs readily if nuclear. That is, cell phone is the that cell phone involves in the loss of by adding of external nucleophile. Amino 1,3 peroxidiols on diazotization, sometimes in nitrosode compounds, is quite stable. It can be converted into diazonium salt by treatment with a good strong base. 1,3,4 oxidiols on heating with primary amines rearrangement gives 1,2,4 oxidiols. Signones. Signones are prepared by the dehydration of N-nitroso alpha amino acids. These compounds were given the trivalent name signones of after the University of the Sydney, which they were discovered. Signones are called as a mesomeric compounds. Signones are 6 pi electrons containing aromatic cyclic compounds. Is also 1, 2, 3 oxidizers like derivatives. Thiodiazoles. These thiodiazoles are four types are there. 1, 2, 3 thiodazole, 1, 2, 4 thiodazole, 1, 2, 5 thiodazole, 1, 3, 4 thiodazole. 1, 2, 3 thiodiazoles. Synthesis of this 1, 2, 3 thiodiazoles by the reaction of thionyl chloride with hydro hydrogens containing an acidic methylene group. 1, 2, 3 thiodiazoles 5-thiol is obtained by the reaction of chloral to cell hydrogen with polysulfide. That is chloral hydrate reacting to cell hydrogen, then gives to cell hydrogen of chloral hydrate. It is involved in the loss of HCl, then undergoes cyclation with sodium sulfide, gives 1, 2, 3 thiodiazoles. Reactions. Thiodiazoles are very weak bases. Electrophilic substitutions are partially unknown. Halogenation and mercylation is possible. Nucleophilic displacement of aromatic ring, anionic ring, or forms rings from ring carbon occurs readily. Amino group on the ring carbon can be diazotization normally. Hydrogen on ring carbon. Hydrogen on ring carbon is hydrogen on ring carbon is replaced by metal. When 5-phenyl 1, 2, 3 triazoles, 5-methyl 1, 2, 3 triazoles reacting with alkyl lithium, then metallation takes place at lithium attacking at fifth position of 1, 2, 3 triazoles. Then it is reacting with carbonyl compounds. The carbonyl compounds are converted to alcohols of the products. And halogen on ring carbon readily react with the metallation. Ultimately, ring cleavage occurs. However, simple however, a simple heteronucleophiles like OH minus and H2 minus displace halogen from ring carbons. And heteronucleophiles attack hydrogen on ring carbon, leading the ring fusion. In the thermal condition, 1 to 3 triazoles are converted into thioketane with the ex- extraneous of the molecule of nitrogen. One to four thiodiazoles. 1 to 5 thiodiazoles. This 1 to 5 thiodiazoles. Synthesis of this 1 to 5 thiodiazole. 1 to 5 thiodiazoles are obtained by the cyclation of 1,2-diamino with sulfonium chloride. 1,2-diamines reacting sulfonium chlorides. Next one is 1 to 5 thiodiazoles are always formed by the reaction of alpha amino carboxylic amide with C, S2Cl2 and alpha amino carboxamide reacting with S2Cl2, they gives 125 thiodiazoles. 125 thiodiazoles, one, one, 1 dicarboxylic acid are obtained by the condensation of sulfonamide with 1,2 diketones. Reactions. Methylation of 1 to 5 thiodiazoles most to be carried out by LDA of if alkyl or aryl lithium is used in ring takes by addition at sulfur. Halogen atom on carbon can be replaced by the nucleophile. One two four thiodiazoles. 134 thiodiazoles. 134 thiodiazoles are obtained by the cyclation of NNS diacyl hydrogen in presence of P2SY. 134 thiodiazoles are also obtained by the reaction with the 134 oxidizole with the P2S5. Reactions. A halogen on the ring carbon is readily replaced by the nucleophile. An amino group on ring carbon is readily diazotization. That E-diazotization ion is reactive in though to couple with mestalines. Deprotection of carbon-hydrogen bond by nucleophiles leads to ring cleavage. Triazoles. Triazoles are five-membered heterocyclic system containing three nitrogen atoms in the ring. These isomers triazoles are possible. 1, 2, 3 triazoles, 1, 2, 4 triazoles. 1,2,3 trizoles. 1,2,3 trizoles are existing two tautomers. 1H 1,2,3 trizole, 2H 1,2,3 trizoles. 2H 1,2,3 trizoles are more stable. Synthesis one synthesis 1,2,3 trizole synthesis. One substituted 1,2,3 trizoles are obtained by the cycloaddition of alkyne with the azide. Alkyl azide or azodeus instead of terminal silane acids may be used. Two substituted 1,2,3 trizoles are obtained by the oxidation of bis aryl hydrogens of 1,2 diketones with the copper 2 salts. One substituted 1,2,3 trizoles are also obtained by the condensation of aryl azides with SL Witting reagents. Properties. In substitution, 1,2,3 trizoles resist N alkylation under normal condition. Under alkaline conditions, alkylation or acylation can take place at 1 or 1/9 position. Second substituted product is predominantly formed. Halogenation occurs steadily. Halogenation when 1,2,3 trizoles reacting with the bromine in 500 degrees Celsius, 4,5 dibromo 1,2,3 trizole formation takes place. And this when one methyl 1,2,3 trizoles reacting with bromine is CCl for heating. Then 4 bromo 1 methyl, 4 bromo 1 methyl 1,2,3 trizoles formation takes place. Nitration. The ring system is relatively resistant to nitration. Nitration of 2-phenyl 1,2,3 trizoles preferentially takes place in the benzyl ring. 2-phenyl 1,2,3 trizoles are undergo nitration with HNO3 H2S for room temperature. Nitration takes place at fourth position of 1-phenyl 2-phenyl 1,2,3 trizole. Then further nitration takes place. Then gives fourth position of 2-phenyl nitro 1,2,3 trizoles. So oxidation and reduction. This ring system is stable towards oxidation and reductions. When uh, when when benzyl and one benzyl 1,2,3 trizoles react with the hydrogen palladium, that benzyl group under reduction takes place, and 4 methyl 2-phenyl 1,2,3 trizoles undergo oxidation with Kl-4. That methyl group on phenyl ring undergo oxidation to form carboxylic acid. Metallation. N substituted 1,2,3 trizoles can be lithiated at fifth position at low temperature. At a higher temperature, ring cleavage takes place. A halogen at fifth position and is possible to metallation. Nucleophilic displacement reaction with the halogen fifth position takes place. Pyrolysis, 1 to 3 triazole undergo pyrolysis, then gives azarine is the product. This is a dimethyl rearrangement. The outside amine NH2 is replaced by the inside NH group. 1,2,4 triazoles. 1,2,4 triazoles are also exhibits tautomerism. 1H 1,2,4 triazoles, 4H 1,2,4 triazoles. This 1,2,4 triazoles, one substituted 1,2,4 triazoles are obtained by cyclodehydration reaction of NN diacyl hydrogens with primary amines. One substituted 1,2,4 triazoles are also obtained by the reaction of bis dimethyl ammonium aminomethylene dihydrogen with primary amines. Reactions N substitution, N alkylation or N acylation preferable occurs at first nitrogen atom. Two the triazoles undergo alkylation and acylation at first nitrogen atom. And fourth alkyl derivatives can be prepared through the fraternization of one acyl 1,2,4 triazoles. Halogenation takes place preferably at fifth position. Diazotization. Lithiation 1-methyl 1,2,4 trizoles on reacting with N-beta lithium. Metallation takes place at the fifth position. This metallation reacting compounds reacting trimethyl chloride. Trimethyl takes place fifth position of 1-methyl 1,2,4 trizoles. Replacement reaction. Halogen and nitro RS and sulfonium methyl sulfoniums groups in fifth position of 1 to 4 trizoles undergo nucleophilic displacement reactions. That is 1H 1 to 4 trizole of fifth nitro compound on reacting with the HCl. Chlorine atom is replaced by the nitro group. Oxidative desulfonation of 1 to 3 trizoles occurs with on treatment of with HNO3. Medicinal important 1 to 4 trizoles are riboflavin, alprazolamine, fluconazole, Raxil, tetrazoles. Tetrazoles are 1H tetrazoles, 1H tetrazoles, 2H tetrazoles. This synthesis, these tetrazoles are obtained by the reaction of nitrile with azides. When nitriles undergo 1 to 3 dipole addition reaction with azides, then gives uh, 1 to tetrazoles will be formation takes place. Imidochlorides react with azides under phase transfer conditions, form one substituted tetrazoles. One substituted tetrazoles 5-thiol are obtained by the reaction of aryl isothionitrile with azides. Isonite, isonite, isocyanates react with N-halosuccinamide and azide to give 5-halo tetrazoles. Next, we need 13 six-membered heterocyclic containing two heteroatoms. So that are we are going to discussing pyridazine, pyrimidine, pyrazine compounds. First, we are going to discussing pyridazine. When this synthesis of that pyridazine, most of the synthesis of reaction between four compound with hydrogen. In some of this synthesis, 1, 2, 4, 5 tetragenes are the starting materials. From malic anhydride derivatives with hydrogen and malic anhydride derivatives reacting with hydrogen, then opening the ring loss of water molecule, then forms uh, dihydropyridazine formation takes place. The dihydropyridazine undergo reacting POCl3 converted to pyridazine derivatives. Next synthesis by involving of reaction between 1,4-dicarbonyl compound with hydrogen. Dihydro derivative of pyridazine formation takes place. This pyridazine undergo air cyclization, aromatization. Pyridazine will be formation takes place. Then unsaturated 1,4-diketones reacting with hydrogen, then forms 3,6-dimethyl pyridazine the product. From 1 to 4, 5 tetragenes and stellines. This 1, 2, 4, 5 tetragene react with stelline, undergo Diels-Alder reaction, then followed by loss of nitrogen gas, then gives pyridazine. Properties. Pyridazine are weak base. They form salts with mineral acids. Protonation of secondary nitrogen is difficult because of the higher energy required to generate two positive charges on adjacent carbon atoms. Therefore, quaternary salts under nitrogen and oxides and hydrogen peroxide. And pyridazine reacting with it checks and alkyl halides and oxidation formation takes place. Electrophilic substitution reactions. Pyridazine are highly resistant to electrophilic substitution reaction. No nitration, no sulfonation has been reported. Nitration takes place at only when electron releasing groups are present on the ring. However, 4-nitropyridazine is obtained readily through the nitration of pyridazine N oxide followed by deoxidation with PCl3. Pyridazine reacting with hydrogen peroxide, N oxide, pyridazine N oxide, then nitration with 4-nitropyridazine N oxide, then last by elimination of oxygen atom and nitrogen, then gives 4-nitropyridazine. So reaction with the nucleophilic reagents, reaction with the nucleophiles like ammonia or organometallic reagents occurs at third position. Alkyl pyridazine undergo condensation with carbonyl compounds in presence of weak bases. Nucleophilic displacement reaction. Hal- Halogen atom on adjacent to nitrogen atom ring carbon atom, then undergo nucleophilic displacement reaction takes place. The reaction takes place by the addition elimination mechanism. Halogenate nitrogen adjacent carbon atom reacting with ammonia, then addition takes place, then followed by elimination of HX. This addition elimination mechanism possible and reduction when pyridazine reacting with sodium ethanol, hexahydropyridazine will be formed, formation takes place. This photochemical rearrangement, pyridazine undergo rearrange to give pyrazine under photochemical condition. pyrimidines. Synthesis of pyrimidine, 1,3-diketones reacting with urea, then gives pyrimidine as a product. And another method is 1,3-diketone reacting with amidine, then gives pyrimidine as the product. Malic acid, when reacting with the concentrated H+4, then gives beta keto acid. Reacting with urea, then gives pyridines. Malanoic ester react with urea, then gives barbitric acid as a product. An alpha beta unsaturated carbonyl compounds reacting with the urea, then gives pyrimidine as the product. Another methods from ketone and formamide. When phenyl methyl ketone reacting with the formamide, then gives beta enamino ketones. This beta enamino ketone reacting with formamide, then gives pyrimidine as a product. From 1,3-diketones and aldehydes and amines. 1,3-diketone, 2 moles of amines, ammonia and aldehyde, then gives pyrimidines. 1,3,5-tetragenes and enamides. 1,3,5-tetragenes and estelins undergo Diels-Alder reaction, then loss of HCN, then gives pyrimidines as the products. Next, following the methods for synthesis of dihydropyrimidines, ethyl acetate reacting with the aldehyde, benzaldehyde, then gives alpha beta unsaturated carbonyl compounds. This alpha beta unsaturated carbonyl compound involves in the loss of water molecule, then gives dihydropyrimidines as the products. Unsaturated acids reacting with urea, then gives pyrimidine as a product. Reactions. Pyrimidines are weak bases, can be promoted by acids. Diprotonation takes place with strong bases. Bromination electrophilic substitution reaction takes place at C5 position. Bromination takes place fifth position. Sulfonation takes place fifth position takes place. Nitration is not observed. Nucleophilic displacement. Halogen atom at 2, 4, 6 position, then displace the nucleophile. Halogen atom at second position more reactive, then fourth position is more reactive than second position, then sixth position. Reaction with nucleophilic reagents. Reacting with nucleophilic reagents like hydrogen, then gives pyrrolizole as a product. Oxidation takes place. Pyrimidine reacting with peracids or hydrogen peroxide, then an oxide will be formation takes place. These anoxides of pyrimidines reacting with acid chlorides, then oxygen atom's elimination takes place. Reactivity of methylene group. Methylene group at second position more reactive than fourth position, then sixth position. Then reacting with the methylene, reacting with the active methylene group, reacting with the pyrimidine, reacting with aldehydes, then chalcones will be formation takes place. Dimorph rearrangement here, that inside nitrogen is replaced by the outside nitrogen atom. Claisian rearrangement, thioallyl pyrimidines undergo Claisian rearrangement. So these are natural occurring biologically important pyrimidines like varinol, luminol, pentatol, sulfonamide, uracil, thiamine, cytosine are the biologically important natural occurring heterocyclic compounds. That is a pyrimidine, pyrazine. Alpha amino carbonyl compounds undergo self-condensation, then gives dihydro derivative of pyrazine. This dihydro derivative of pyrazine undergo loss of hydrogen atom in presence of air, then this pyrazine as the products. One diamines reacting with ethylene diamine reacting with one comma two dicarbonyl compounds, then gives one dihydro derivatives under air, then gives pyrazine is the product. From azerines, when azerines in presence of sunlight, they gives uh, then gives a charged compounds. These are undergo self condensation, then give dimerization. They gives pyrazine is the products reactions. Pyrazines are weak bases. Pyrazines undergo diprotonation in strong acids and in oxides. Pyrazines are converted into amino mono and dianoxide acid. Electrophilic substitution reaction takes place at adjacent of nitrogen atoms. Nucleophilic displacement reaction, halogenate nitrogen atoms in position. Then nucleophile outside nucleophile replace the halogen atoms. Reaction with organometallic reagents.